The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang, a fossil of light dating back nearly 13.8 billion years. It was released when the early universe cooled just enough for protons and electrons to combine into neutral hydrogen, making the cosmos transparent for the first time. These photons have traveled ever since, stretched into microwaves by the expanding fabric of space. The CMB isn't uniform. It contains minuscule temperature differences that encode the earliest imprints of structure in the universe. These tiny ripples became galaxies, clusters, and vast filaments. Modern telescopes like WMAP and Planck have mapped the CMB across the entire sky, revealing astonishing detail about the universe's age, curvature, and contents. By studying this ancient light, we can look back to the moment the universe first became visible, a cosmic snapshot frozen in time, still whispering its secrets across space. True or false? The cosmic microwave background was created before the formation of atoms. False. The CMB was released after neutral atoms formed, during the era of recombination. What process made the universe transparent, allowing the CMB to be released? Recombination. Fill in the blank. The CMB was emitted approximately blank years after the Big Bang. – 380,000 years after the Big Bang. Fill in the blank. The fluctuations in the CMB temperature are about 1 part in blank. $100,000. Fill in the blank. Photons from the CMB have been stretched by cosmic blank. Redshift. True or false? The CMB proves the universe was once hotter and denser than it is today. True. Fill in the blank. The cosmic background radiation was accidentally discovered by Planck and Wilson in 1965. Penzias and Wilson in 1965. Which mission first detected temperature variations in the CMB? Cosmic Background Explorer, also known as COBE. Fill in the blank. The CMB provides strong evidence for the blank model of the universe. The Big Bang. True or false, the CMB can only be detected in specific parts of the sky. False, it fills all of space and can be observed in every direction with the right instruments. Fill in the blank. The surface of last blank describes the moment photons could finally travel freely. Surface of last scatter. What is the approximate current temperature of the CMB? .7 Kelvin. Fill in the blank. The CMB is a snapshot of the universe when it was just blank old. $380,000 years old. Fill in the blank. The satellite that provided the most detailed CMB map to date is blank. Planck. How does studying the cosmic microwave background help scientists understand the early universe? Studying the CMB gives scientists a direct window into the conditions of the early universe, just 380,000 years after the Big Bang. Its uniform glow and tiny temperature fluctuations encode critical information about the density, composition, and expansion rate of the cosmos at that time. These patterns help cosmologists understand how matter began to clump into galaxies and how the universe evolved over billions of years. Precise measurements of the CMB also allow scientists to calculate the universe's age, test inflation theories, and determine whether the cosmos is flat, open, or closed. In essence, the CMB is the universe's baby picture, and it still holds clues about its ultimate fate. True or false? The CMB contains tiny temperature differences that help shape the universe's large-scale structure. True. What physical feature of the CMB helps scientists understand the universe's geometry? The angular size of its fluctuations. Fill in the blank. The small fluctuations in the CMB help seed the formation of blank. Galaxies. If the CMB was released 380,000 years after the Big Bang, and the universe is now approximately 13.8 billion years old, how long has the CMB been traveling through space? To calculate how long the cosmic microwave background has been traveling, we subtract the moment it was released, 380,000 years after the Big Bang, from the universe's current age of 13.8 billion years. The result is nearly 13.8 billion years, the age of light itself. Which of the following best describes how the CMB looks across the sky? A uniform glow with subtle variations. If the CMB photons have been traveling for 13.8 billion years at the speed of light, what is the maximum distance they could have traveled in kilometers? To calculate how far the cosmic microwave background has traveled, we start with the speed of light, 300,000 kilometers per second, and multiply it by the total time since the CMB was released, which is 13.8 billion years. Converting that into seconds gives us about 4.355 times 10 to the 17th seconds. Multiplying those together, we get a total distance of roughly 1.307 times 10 to the 23rd kilometers. That's the maximum distance this ancient light could have traveled, marking the boundary of the observable universe. True or false? The CMB is currently visible in the visible light spectrum. False due to redshift from cosmic expansion. The CMB now lies in the microwave part of the spectrum. Fill in the blank. Due to cosmic expansion, the wavelength of CMB photons has been blank over time. Stitch. What role did the Planck satellite play in studying the CMB? It mapped the CMB with unprecedented accuracy. Fill in the blank. The CMB is observable today with microwave-sensitive Planck. Radio telescopes. True or false? The discovery of the CMB contradicted the steady-state theory of the universe. True. Fill in the blank. The polarization of the CMB can provide clues about early blank waves. Gravitational waves. Why does the CMB support inflation theory? It shows quantum noise was amplified. A microwave telescope scans a full 360-degree sky map of the CMB in 24 hours. What is the average angular scanning speed in degrees per second? To find the angular scanning speed of a telescope mapping the cosmic microwave background, we start with the total angle of coverage, 360 degrees. We divide that by the total time of observation, which is 24 hours or 86,400 seconds. Dividing 360 by 86,400 gives us approximately 0.00417 degrees per second, the slow, precise motion needed to track the oldest light in the universe with accuracy. How did you do? Tell us in the comments below. And thanks for watching BrainyKidz. We hope you had fun learning today. Don't forget to like, subscribe, and hit the bell so you never miss a new quiz. See you next time, Brainy friends.